Okay, let's get started. A little technical difficulty getting the microphone working. We have a lot of visitors. Welcome if you're here from high school and wanted to try an electrical engineering class. So I mentioned last time that convolution, so convolution is sort of the pinnacle of Fourier transform properties. We have this convolution rule that becomes multiplication in the frequency domain. But if you have two periodic signals, then convolution kind of goes out the window. So let's start by assuming we have, by talking about convolution for periodic signals. And we notice that when you plug in the convolution formula, you get something that's not meaningful, right? So let's let x of t and y of t both have period cap t. Okay, so if you plug in this type of thing, x of t convolved with y of t, and you get this integral. Oops, tau there. What's wrong with this? Why do I say it's not meaningful? What? It's going to be infinite, because this thing in here is still going to be periodic. So you're going to have an integral from negative infinity to infinity of a periodic function. That's going to be infinite. Okay, or 0 or something. It's not going to be very interesting. It's not going to be a function of t. Okay, so, but let's define a new type of convolution that we call circular convolution. Put a circle around it. And here we'll define it for the period t. And all we're going to do differently is rather than integrate from negative infinity to infinity, let's just integrate over one period. Okay, I'll put that like this. So any integral over any period is going to be the same. You can go 0 to t if you want. Well, it's a period, we assume they both have period t, so let's use that same period. Okay, so the product will also be periodic with that same period. Okay, so this is a different thing. It's not, I mean, we had a reason for convolution, right? Convolution was what any linear time invariant system did. And now we're defining something that's just kind of arbitrary. Let's see how it relates to convolution to begin with. Okay, so if you had, I'm going to give several equivalent ways of thinking of circular convolution. You can think of any one you actually want for the situation you're in. Okay, so let's now we'll take our periodic signal, take one of them, say y, and let's define a non-periodic signal, y tilde of t, that's just one period of y of t, and 0 everywhere else. Okay, so if we had something like this, if y of t was like, sorry, I'm not perfect at drawing those. Oh, I actually repeated it pretty well. Okay. All right. And what we would do, so clearly t is something like this here. Okay. And what we're talking about is let's let y tilde be, just take any one period. Boy, this computer's being glitchy, like always. So y tilde would be like, oh gosh, I have to trace over. Be like this. And then it would be 0. 0 everywhere else. Okay, so it's just one period of this thing. All right, now if you did a convolution of y tilde with x, so x of t convolved with y tilde of t, that is actually going to be exactly equal to our circular convolution above. Okay, so that's one way to think of circular convolution. It's just one of them has been reduced to a single period. All right. And now it's regular convolution. Now, let's talk about why do we need to discuss something other than convolution? We already said if we have two periodic signals, convolution doesn't make sense. But maybe that means we just should never be considering convolution of two periodic signals. However, we have a convolution rule for continuous time signals. Convolution in time is multiplication and frequency. We would like a similar rule for the other variants, for discrete time or for the Fourier series, right? Already we know Fourier series deals with periodic signals. So without a notion of convolution for periodic signals, then there would be no such rule for the Fourier series, right? If we go to discrete time, we have a multiplication rule. In continuous time, the multiplication rule is dual, right? So it says multiplication in time is convolution in frequency. Now you go to discrete time and you say, okay, multiplication in time makes sense, but convolution in frequency is not going to be meaningful anymore. Why is that for discrete time? Because discrete time Fourier transforms are always periodic. Okay, so that rule is going to have to change somehow. And the cool thing about it is that the change to the rule, so here are Fourier properties, aside from the continuous time one. We have discrete time. In discrete time, we have the following, that the multiplication rule goes like this. It says that xn times yn under the Fourier transform is going to go to xf circular convolution with yf. Now, when I defined circular convolution above, I said I should specify what the period is. Well, what's the period here for the Fourier transform? Is 1. All right. Okay. So this is actually the multiplication rule for discrete time. It's almost the same, but you have to do circular convolution. All right. Another rule we can look at. Can look at the continuous time Fourier series. And here, of course, now we're going to look at a convolution rule. I'll call it the circular convolution rule. And here it says, let's assume x of t has Fourier series coefficients ak. And let's say period t. Y of t has coefficients bk, let's say. Okay, so some sequence. Then we get that x of t convolved with y of t should be something like multiplication. And it is. It's ak times bk. Let me just show how it's different than this. There's a normalization over here by 1 over t. And this is actually circular convolution. Okay, so that's the rule. Right. So wherever you would think that you use convolution in one of these properties, if you know it's periodic, like it would always be in the Fourier series, then you know it's circular convolution. Okay, so let me give a few more ways of thinking about circular convolution or computing it. So sometimes you have two finite duration signals. Okay, and you would talk about doing a circular convolution of these. So let's say their duration is cap t in this case for both. Circular convolution, you should always have them matching in some way, either the same period, same duration, something like that. Okay, so here's an example. Here's an example of some finite duration signals. Here's one that goes from time 0 to time cap t. And maybe another one that looks like this from 0 to t. Okay? Now, if you did... Okay, so circular convolution will result in a signal that is the same length of what they started with. So maybe we should first talk about what would happen if you convolve these regular without doing circular convolution. All right. So let's on the side here do regular convolution. Now, regular convolution, we're going to have to interpret that these finite duration signals have 0 everywhere else, right? You have to have signals defined for all infinity to do convolution. All right. So assume it's 0 elsewhere. And by the way, if you used MATLAB and you just define 2 vectors, those are finite length signals, and you use the convolution function, it's going to assume that it's 0 everywhere else. It's just an implicit assumption. What happens if you convolve 2 vectors, say in MATLAB? What happens to the length? Let's say you start with 2 signals, each of length 10 samples, and you run a convolution. What do you get back in terms of the length? What? 20. Yeah, it's going to be like 19 because of just how it matches up. So you get double the length back, right? Okay, so that's already different than circular convolution, where we're going to get something the same length back. In regular convolution, you get something longer. Okay, so let's see, how do we do it with the flip and shift method? So you would get let's keep the first one not flipped. So this first one went like this. And the second one we flip in time. So it's something like this. Right? And then we shift by little t. So for each shift, so this is y of t minus, well, this is just y of negative tau. This is x of t. Of course, when you incorporate, when we want y of t minus tau, so that gives us a shift. So we see, for example, of course, then you calculate integrals. I'm not going to go through the exact expression. The answer should be, first of all, they overlap for what range? So this is similar to the question I asked a minute ago. What ranges of values little t will cause these to overlap and get a non-zero integral, potentially? Yeah, so it starts at 0. And then if it was up to, exactly, if we shifted it all the way by 2t, then it's going to go from here to here. And they won't overlap again. So between 0 and 2t, you might get non-zero outputs. And that's all I wanted to work out for that example. I mean, the convolution is going to go up and then down and something. Okay. So in a cartoon answer, it's something like this. From 0 to 2t, maybe it goes like, who knows, something like that. Okay. All right. And as we mentioned, so this is the key of what I wanted to mention about regular convolution, that you get output values on some range, like double the length. And for discrete time, you get 2n minus 1 is the length, right? If they both were length n. Of course, for regular convolution, they don't have to be the same length. But for circular, they do. So let's go back over to circular convolution stuff. That was regular convolution. Okay, so what we're going to do for circular convolution is just x of t convolved with y of t is going to just be defined the same way as if you took the periodic extensions of x and y and did circular convolution as I already defined it. Okay, although I'm going to express it in a different way here, but it's exactly that same thing, right? Just extend x and y with repetitions and do circular convolution. But you can say it this way. You can say the integral of x of tau, y of something here. I'm going to use a sort of odd notation for these continuous numbers. So it looks just like the convolution integral from 0 to t, except what I'm saying here is subtract off multiples. So add or subtract multiples of t, of cap t, to make the argument within the range 0 to t. So in other words, choose any k, integer k, such that this is in the range 0 to t. That's like defining a periodic extension. Okay. But we can do a flip and shift here for circular convolution. There's a flip and shift method, and maybe the name matches up with this technique best. I know last time when I mentioned circular convolution, you said, oh, circular implies you wrap around. And that's what this flip and shift method is going to show. So if you go like this, take those two signals. Okay. Now we're going to assume that we have, I'm going to draw these green lines like this, showing the range of our finite duration signals, the domain. And we're going to assume anything that leaves, as we do a shift, anything that leaves this gets wrapped around to the other side. So so that's our x of t, our x of tau. Now for the y of negative tau, let's say for t equals 0, we said, of course, it goes like this, right? But wrap it around. So since it's off the left side, then we bring it over here. Okay. Now, as we shift, so that means y of, let's say, t minus tau, because we're going to have to do this for every shift, right? Is going to be, let's say t is some small positive number. Then it would be like this, right? When you shift it, t minus tau. But all of this stuff that came off the edge, just wrap it around. So we're always integrating. We're doing our multiply and integration between 0 and cap t. So we're taking our x of tau. We're multiplying it by this flip and shifted signal. But the shifting just wraps around. Okay? Okay, and as I said a minute ago, but I'll just write it here, that this is all equivalent to defining the periodic extensions and doing circular convolution on the periodic extensions. Okay, there's even, let's see, maybe one more way I can think of circular convolution of finite duration signals. Here's a final way. Do regular convolution. We have a little demonstration of what that means over here. Do regular convolution. You get a signal that's too long. Okay? Then take everything after cap t and wrap it around and add it in. So in other words, everything that leaked over past outside of the duration 0 to t, you have to just circle it around and add it in. It superimposes on itself, wrapped around. So all these things give the same answer. Okay, they're all different ways of interpreting circular convolution. Okay, so I want to give a little bit of justification for why. Well, actually, I think I'll first do a little demo. I have a MATLAB demo here. Okay, so this demo is going to use, I'm going to show the multiplication rule and how it really becomes circular convolution, and I'm going to do it by, in a way that'll be something maybe you've tried in your lab already. Maybe this will help you understand what's going on a little better. So It's running. Just a minute. Just a minute. Spoiling the fun. Okay, so here's what I've done. I start by just creating a very simple signal here. This is just a sinusoid that gets cut off at a certain time. So the first half is a sinusoid. It's at a frequency of 0.1. And then all of a sudden it stops. Okay, the second half is 0. So in the frequency domain, if we took a Fourier transform, right, you get this, as you'd expect. You know, it looks a lot like the Fourier transform you expect of a sinusoid. I didn't label the horizontal axis correctly here. Okay, this is 0 frequency, and in discrete time you always go up to a half, right? So it's 0 to a half, negative a half. So you see that these peaks are at 0.1. All right. Now, if it was just a sinusoid that didn't stop in the middle, then it should be perfectly just delta functions in the frequency domain, right? But you see these aren't perfect delta functions. They kind of leak over to neighboring things, and there's a reason for that. In fact, the specific pattern here actually carries some importance. What does it tell you? Yeah, it's a sync pattern because why? What does it correspond to? The fact that this sinusoid stops. You know, this isn't just a sinusoid for the whole time duration, right? It stops at some point, and that has to somehow be carried in the frequency representation. So, as was mentioned here, this is like multiplying a sine wave by a rect function. So in the frequency domain, it should be like your delta functions convolved with a sync. That's why this looks sort of sync-like. Okay. Anyway, the idea is this. I'm using a discrete Fourier transform here, right? So that's both discrete time and discrete frequency, or you could think it's a periodic. It's discrete time and it's periodic in time. You can think of it like that. Of course, you know, you look at the graph. You look at the graph and you say, well, that's not periodic in time. Well, the DFT interprets it as if it's periodic. Okay. But what that means is, what if we try to filter this? What if we try to manipulate it by changing the frequency domain directly? Okay. I'm going to do a very simple change in the frequency domain. So here's the DFT of the original signal. Here, you see I've changed it slightly. What I've done is I've just zeroed out all frequencies above something a little higher than 0.1. Okay, I've made some threshold. This is a low-pass filter. Right? I've kept everything the same, but I've zeroed everything higher than some frequency. So I still have so this should change my signal in some ways, right? It's a low-pass filter, so it should smooth out the signal. So now let's go look in time what this did. Well, first of all, zeroing out part of the frequency domain, that can be considered a multiplication. All right? So this is multiplication in frequency. So what should it be doing in time? Convolution with some sort of smoothing filter. So let's go look at what happened in time. Here's the inverse Fourier transform of that. Still roughly the same, but as you notice here, it doesn't cut off abruptly, right? There's a big difference between how it started like this, it just cuts off abruptly, and how it became after this filtering. It kind of dies off, right? There's some ringing. Okay? So that's what we expect in a convolution. But how can someone see in this graph some evidence of a circular convolution? Yeah. Yeah, you get this here. If this was a convolution, you wouldn't expect out of nowhere just some blip at the end, right? It would die off around here. It would, but what's the cause of this? It's that we have circular convolution. So the filtering at this first edge, it's kind of like it's going from 0 to a sinusoid. The filtering that would leak over this way wraps around. Okay. So in fact, filtering, and we'll talk more about filtering next time, but filtering using the Fourier transform is a common technique because the Fourier transform is an efficient algorithm. You can do it, you can do it quickly on long block lengths, faster than explicitly doing convolution digitally. but you have to take into account that when you do this, you're doing circular convolution. So in fact, when these are implemented, like when digital signal processing is implemented using the Fourier transform, there are techniques used. You put little buffers around, you pad zeros around your signal, you catch the part that wrapped around, and you handle it correctly so that, in fact, you're implementing a true convolution. If you're not careful, you would have these artifacts when you try to do filtering in the frequency domain. Okay. Great. So I want to work out a demo for circular convolution, and then we'll move on to another topic here. All right. Where did my pen go? I always set my pen down somewhere in front of me. Pocket. No. Did anyone see where I put my pen? Where did I? Did I throw my pen? Where is that? No, it just vanished. This was it was actually a magic trick. I've been trying to distract you so you wouldn't see where it went. Oh, no. Ah, it is down there. No wonder you couldn't find it. All right. So let's do a discrete time convolution that we can actually work out here. Let's use blue. Okay, so let's define xn is just a signal with four numbers. Okay, so it's So it's 1, 2, 1, 0. Okay. Let's say yn. Same duration. Duration n equals 4. All right. So we have 0, 1, 1, 1. Keep all the numbers very simple here. All right. You can think of these as just vectors. I can write xn as just a vector if I want. 1, 2, 1, 0. Y equals 0, 1, 1, 1. All right. So finite duration, discrete times. Signals. Now, we want to calculate Zn equals the circular convolution of xn and yn. All right, so what we want to do is flip y. So let's say for z of 0, we have just y of negative k wrapped around. All right, so it would be 0, 1, 1, 1. But we're going to wrap it around here, so we get 4 minus, negative 1 becomes 3. Well, by symmetry, this is going to look very simple, right? All right. Oh, I didn't do this to scale. Sorry. I like to line these up. Just imagine that these are lined up. Okay. So multiply them and add them up, right? Multiply the x up here and this y of negative k. So this x of k, let's say. All right, so we get just the sum of the 2, the 1, and the 0. So it's 3. All right. Then we want to calculate z1. And what we're going to do is shift this whole thing to the right by 1. So we're going to get 0, 1, 1. This is at the indices 0, 1, 2, 3. Of course, then 1 shifts in from the left there. Okay, so now we take this one. This is y of 1 minus k. I'm going to, 1 minus k mod 4. Okay. So that, so now we get the sum of 1, 1, 0. So we get that this equals 2. Let's do z of 2 equals, again, I think you get the idea here, the signal. So this becomes y of 2 minus k mod 4, which is 1, 1, 0, 1. So now we sum up, multiply that by the x signal, we sum up 1 and 2 and 0. So we get 3 again. And then we just have one more to calculate. Z of 3. And I think you get the idea. It's going to be 1, 1, 1, 0. All right. So now we sum up 1, 2, and 1. So we get 4. All right. So there's our result. If we want to plot it versus n. Then z looks, the output of this circular convolution looks like this. 3, 2, 3, 4. And we could have just done a regular convolution, which would have become a longer length signal, and then just wrap the result around. We'd get the same thing. Okay. All right, let me justify a little bit about why circular convolution is the right rule for something like, for example, discrete time multiplication property, let's say. Well, first of all, why does the regular rule not generalize? We have convolution in continuous time. Why does it not work for discrete time? I mean, we already said that you can tell because the Fourier transform is periodic that something has to change. Okay, but remember that we can take any discrete time signals and we can, so let's say we have a product of two discrete time signals. We can always interpret these as continuous time signals by saying this is a sum of delta functions. And the delta functions are each scaled by the values of this discrete time signal. Okay, so this is like our continuous time version of a discrete time signal. It's just delta functions instead of a sequence of numbers. But notice that if under this interpretation, if you convert them both to continuous time, now you're going to have a product of delta functions. Okay, we do not deal with products of delta functions. We've mentioned that before. So already we see that, okay, multiplication of discrete time signals, when you interpret those in continuous time, you're multiplying delta functions. We're not going to try to do that, so we're not going to be able to carry the properties over directly. However, if what we do is we say, let's convert xn to a discrete time signal, and let's create something new here for y. Let's make this the interpolation of yn. So rather than make it a bunch of delta functions, let's just make it a continuous time signal that happens to equal yn at all the integers. Okay. Well, now this would be well defined because this is just a nice function, no delta functions. We multiply it by this sequence of delta functions. Multiplication is going to behave just like we want it to. We're going to end up with, when we multiply these, we are going to end up with, so let's say let's say we multiply these things, then that's going to equal xn times yn times delta of t minus n. That is the continuous time version of what we want, the multiplication. So this is sort of the right thing we should be thinking about. Okay, so that means in the frequency domain, so this is, let's say in the frequency domain, this is just what we expect. That's x of f. Okay, but this here is, what's one choice of interpolation we could use? We could do sync interpolation, for example, which would be a low-pass filter. So then this yt is one period of y of f. Okay, if we did a filter on it, right, if we interpolated. So that's great, because this is like, did I have a name for that? Yeah, I said at the beginning I used tilde to represent just one period. So let's use it here too. One period. Now we actually are doing convolution. But that is circular convolution. So this, let's just say, yeah, it's just what we called it above, one period of YF. Okay, any questions about this? I'm sort of giving you actually a derivation, but I'm going through it very quickly because I just want, I just want you to have some sort of understanding of why the rule changed. The rule had to change because you can't multiply these delta functions here. But there's a way to get around that. If one of them you don't turn into delta functions, you instead interpolate it, then you're getting actually the multiplication you want. But what's going on in the frequency domain is you really only have one period. So you're doing a circular convolution. Okay. We could come up with a similar justification for why the Fourier series has the circular convolution rule. Yeah. So actually, any interpolation will work, but if you do it with sync functions, it'll be easiest to understand. Okay, because we know sync interpolation. Yeah. Sample it, exactly. So it doesn't even matter what interpolation you use, but if you do something else, it's not so easy to show that you've done a circular convolution. Yes. Yep. You just need some nice continuous function that matches the samples. Okay. Good. So let's now move on to talking about something else. So we're done with circular convolution. So let's say, how does phase affect the signal? So usually when we're analyzing signals in the frequency domain, we often focus on the magnitudes more than the phase. Okay, we did for Shazam, for example. When you built Shazam, you used the magnitudes of the spectrogram. You didn't care about the phase. So does phase not matter? Well, I'm going to show you a demo here that may surprise you. So let's go back. Let me run my phase demo. Okay. What I'm doing is I'm going to read in a sound. And it's not very long. And here's the spectrogram. Okay, here's time. Here's frequency. Can anyone tell what the song is by looking? No. All right. If you're really good. Just kidding. All right. Here we go. Wow! I feel good. Sorry that the volume cord doesn't work very well here. Let's do that again. Wow! I feel good. Okay. Take that. All right. As I said, this is the spectrogram of it, so it's showing the frequency domain versus time. Right? There's his talking. You can see talking is different than instruments. Okay. So now I'm gonna mess with the magnitude and I'm gonna mess with the phase. Okay. First, I'm gonna mess with the phase. I'm gonna take a Fourier transform. This is all done in the code. Don't worry about Well, okay, I'll just show you a little bit. I take the magnitude of the Fourier transform, I take the phase of the Fourier transform. Now, first I'm going to give it a 0 phase. So I'm just going to replace the phase by 0 and now do an inverse. So I've zeroed out the phase. The next thing I'm going to do is I'm going to do a random phase. The random phase means I just put random numbers. I make sure it's symmetric because I need to get back a real signal. Okay. So all of this is just making sure it's symmetric. Okay. Now, next I mess with the magnitude and leave the phase as it is. So first thing I do is I make the magnitude flat. So it's a constant. 0 would mean we'd have a 0 signal, but I make it like 1. Okay. So we lose all the magnitude information of the song. And lastly, I'm going to put in random values for the magnitude, but I'm going to make them positive. That's all I'm doing here. Okay. So, and then okay. So which one of these modified do you think will sound the best? Let me just give you two choices: random phase or random magnitude. You think random magnitude is best. Why is that?
I don't know. I feel like it would just like sound a little bit like the volume would just be different for each like moment. But then other than that, it would.
Okay. Yeah. Good point. So the phase, yeah, you lose all your timing information if you lose the phase. And that's really what you want to get out of this demo, is that, I mean, intuitively, maybe some people would guess that if you lose the magnitude, you won't be able to tell what song it is. So let's listen to them each. What do I call it? Call it 0 phase, rand phase. Okay, there we go. Let's do 0 phase. Oh, I think it's that I scaled it. I need to turn the scaling off. Okay. 0 phase actually does something a little worse than random phase. Random phase at least will sound kind of like there's no timing in the song at all. But, I mean, just like the sound, it's like you had a tube with noise going through it, and that tube was designed to sound like I Feel Good, as close as it could, right? It matches the spectrum. All right, so the 0 phase is funny because it kind of lines everything up at the beginning, actually. It like concentrates the energy at certain places. So it doesn't match the song at all, but it like starts and ends louder. Weird, huh? Okay, now let's do where we change the magnitude and leave the phase intact. So that was flat spec. That's what it was. Okay, so just make it 1 in magnitude. Oh, now I do need to scale it, see, because sometimes the amplitude changes a lot. I should turn it up so you hear it better. Okay, if I turned it up, but I'm sorry that I think I've maxed this out. If it was a little louder, you'd say, oh, it's just noisy. It's the same song. All right, let's do the random phase. I'm sorry, random magnitude. They're actually very similar. This is just a little noisier. So you actually hear the song just fine. Okay. So why is it that you didn't need phase when you made Shazam? If phase tells you all the timing, of course you need to know the timing if you're gonna match songs. Yes, exactly, because you already took time into account by breaking up into short time Fourier transforms. And that's why that's a very popular technique, to use the short time Fourier transform. You want to have some time and some frequency understanding. And so it's popular to say, well, let's explicitly do our time understanding first. Once we get it to a short enough segment, then the phase within there really is not, for sound, it's not noticeable to most people's ears. Okay, it's just kind of the larger scale timing that matters.